Thank you for the organization of this event. My name is Vahid Akhavan. I am the Global Application Engineering Lead at PulseForge, and I am joining you all from West Coast of the United States. Unfortunately, I couldn't be there in person this year, but looking forward to meeting you all on future events. Today, I want to discuss our capabilities at PulseForge to attach components onto temperature sensitive substrates and how that has revolutionized the way we think of electronic manufacturing. So PulseForge, we're a company out of Austin, Texas. We have had we have had a lot of innovations throughout the years. We were better known with our predecessor, NovaCentrix, which is still in the printed electronics business, but we have diverged from this group to enable us to focus on this process of digital thermal processing, which I'll explain. Form, what we're doing is we're harnessing the power of light, in this case of pulse light, to do work. This is a very early on experiment that we would do where we could use a flash of a single high powered flash of a standard camera to reduce the resistance of a printed circuit by twofold. So what we have in this case is we have a circuit that's around 35 ohms in resistance through a simple around 1 the day. What we're able to deliver is we're able to deliver flashes of light that enable us to do work. So what that means is that these flashes of light enable us to heat up layers within a device stack in a non-equilibrium fashion in such a way that we can heat up specific layers that we're targeting beyond the thermal damage threshold of materials, other materials that are in the thermal stack. So we can do interesting work, enabling us to get value and performance out of materials that are really not viable using other types of processing techniques. So in this case, on the top right, we have a cartoon of how the coating in this case is heated up with a more complex pulse structure than the single pulse of the camera flash you saw in the beginning to really get a lot of the best kind of conductivity out of that film. Bottom right, we can keep track of the kind of the resistivity drop after each of these small pulses that are applied to the film. So really, the technology, what it comes down to is this temporal control over light in terms of both power, but also maybe more significantly of control of what is the energy output per time. So what we can do is we can create all sorts of different thermal environments and exposure environments that enable us to get the best value out of our system. So in this case, there are 3 different pulse structures that are demonstrated here, but really the type of kind of control over pulse structure that we have is unmatched with any other types of flash technology, but also any types of really power delivery system. So that's, to a large degree, we call that digital thermal processing. It's a non-contact, very fine control over a very high power exposure. So there, because of this control, the PulseForge tools are used in a wide range of different industries and wide range of different works. For this presentation, I wanted to highlight a few R&D development works. So these are all published manuscripts that have been done using our tool, so we can have a wide range of applications from anywhere from semiconductors all the way out to 3D printing and photovoltaics. We have done a lot of work in semiconductor processing and wafer handling, and we can do a lot of interesting types of curing of polymers and curing of other types of kind of coatings other than just conductive traces for printed electronics. So we can bring a whole complete solution for processing of different layers that go into a modern circuitry. What additionally we can do that is the bulk discussion today is the ability to use these lights to selectively heat up and solder components onto temperature sensitive substrates. So this is key because to a large degree in printed electronics, we could do very well with getting the conductive circuitry figured out. But we had an issue with attachment of commercial components onto the electronic circuitry. And really to create a hybrid electronic, to compete with the electronics that are out there, we really need to have a performance that's as close or exceeds what we can currently produce in conventional electronics. So really what we needed to do is we needed to create a platform where we could bring in commercial components and attach them to circuitry that's already there on these temperature sensitive substrates. And this is the key here in enabling us to get to the next stage of development of electronics. So what you saw in the video on the left was a cartoon of what I'm talking about. So we can have solder, which is the used standard for electronics. So there has been discussions of there has been work with anisotropic conductors, but they cannot match the reliability and scalability of solder paste in their deployment. So what we can do is we can bring in components, we can place components on printed solder paste, and with a few flashes of light, we can solder, reflow that solder and make a good attachment. So here's a real life example of what that means. So you can see this is actual correct time. So within 2 seconds, we can melt the solder paste, we can activate the flux, we can reflow the component into space. There are a lot of advantages with this process, and I'll touch lightly on a lot of them. But one of the advantages is that now we no longer have a lot of movement of air around. So movement of air is not delivering the heat. So we can do this type of processing on a 3D geometry rather than just a flat surface. So that's an interesting work that has been done. And the speed and the kind of the floor plan and the way the system is built, we get a significant reduction in both energy usage in the soldering step as well as the space usage in the production environment. So when we look at what the controlling parameters are for this process, it's no longer a simple kind of pulse power or pulse energy. It's really a combination of the length of exposure. So how long are we exposing the full system to, and the average radiant power output of the lamp. So really, this comes to a key in that these types of tools can deliver up to around 70 watts per square centimeter over second long time scales, enabling us to get these processes going and get them. If you were to do an exposure that's a low in power for a very short period of time, obviously we would have no reflow. If you were to do a very high exposure time for a very long time, we would pretty much burn everything. It's similar to sitting on the surface of the sun for a very short period of time. So you really want to control that. So the temporal control over the energy output is very significant. To really benchmark this process, we have done IR camera measurements of the process itself, and here's an example of that, showing the chip component on the previous page of how we have measured the temperature output, and we can do a good assessment of going at and doing these controlled measurements where we can see that at the reflow temperature we see this discontinuity in the temperature that's associated with melting and resolidifying of the solder paste. And we can obviously get overexposure and burn everything, or we can have underexposure and not meet that reflow temperature. So it's very important to dial in those the process parameters necessary to solder components onto. So with this, we can do all versions of solder. So because now we're looking at a non-equilibrium process, we can look at processing, for example, SAC solder on PET substrate, where the SAC melting point is significantly higher than the damage threshold of the PET substrate in the reflow of it. So what we can do is we can create all sorts of process parameters. So these are some examples of evaluation of these materials on kind of chip components. So you can see that we form good intermetallic formation. We can form very good fillet formation on the solder paste, and these are indicative of a process that only took less than 2 seconds. So it's 1.2 and 1.4 seconds. We could get relatively good outcomes out of these. So you might ask, well, standard reflow process goes through a 10 to 20 minute kind of cycle time. How are you getting this? So the key is this, the fact that we have this really good control over temperature, and we really can activate a lot of these fluxes within a short time frame and really not need to rely on a long soak time to get. So this is some examples with chip components where we have line of exposure to the junction. We can do a lot of work with components that we do not have line of exposure to the junction. And here's an example of a QFN that's been exposed with a large central grounding plane, and we could get relatively excellent soldering happening here with very minimal void formation. We can also look at BGA components, and we can do soldering of components that have, again, the component, the junction is not exposed to line of sight for the light, but we can control the temperature in such a way that we are able to solder those components all at the same time without really thermally heating the underlying substrate. So this is the key in ability for us to solder without damaging the underlying thermally sensitive substrate. So our main focus is on vapor level chip packages. So we work a lot with bare die components and small package components. So we have a very good track record of getting these done on a lot of different substrates, but for the purpose of this presentation mainly on PT. We can do other types of more complex solder joints as well. We're not tied to just soldering of components. So here's an example of soldering of different array of connectors that might be useful for full device fabrication on these temperature sensitive substrate. And we can do these without really damaging the underlying substrate. One of the benefits of this process is that because it's a line of sight exposure, only the stuff that gets exposed heat up. So if we are able to, we have very fine features, we have been able to mask parts of the device that we would not like to heat up. So there's a lot of play there to enable us to get very high value for different types of connection types.
Vahid?
Yes.
Just one, it's 5 minutes, less than 5 minutes.
Yeah, I am last 2 slides.
Okay.
So we can kind of say, well, there's other types of soldering techniques out there. So we're comparing how we can, how does the photonic soldering space lines up with reflow solder, where you have a relatively limited set of components and well, not components, relatively limited set of substrates that you're able to use, where you have you can use a lot of different components, off-the-shelf solders, and very low defects. In laser soldering, you have the opposite end of the spectrum, where you can use various types of substrates, but you're limited in terms of what component sizes and the solder paste you can use. In photonic soldering, we have the best of both worlds. We can use a wide range of different substrates. We use off-the-shelf solders, and we can use a wide range of different components that are used in the process. Here's an example of an LED array that contains 288 LEDs on a board. We're going to use SAG solder. This is copper traces on PT substrate. So we're going to, this is real time application of this. So it's a live presentation. We're doing stenciling of the solder paste here. We're going to move the board into a pick and place component. I'm pick and place the 288 components. It's going to take a little bit to pick and place that many components, so I will fast forward a lot of it, but you can see that it works in a very similar fashion to what you would expect in a standard reflow process. So 90% of the video was the pick and place. So here's the processing type. So we went from the pick and place, the tool is fully off, we turned it on, we processed it, you have a product on the other side of the line. So the processing only takes a few seconds to do, and now you have very much reflowed solder. And because the overall thermal load on the substrate is low, the substrate is cool to the touch, so you can pretty much pick it up and handle it right afterwards. There's a lot of benefits of this process. So I won't go into a lot of details, but one of the keys that we didn't talk about today a lot is the fact that we can, similar to what we have in reflow ovens, we can take advantage of a lot of the chemistry and specificity that's built into solder paste. So one of those items is self-alignment, which is an important feature as we go to smaller sizes. So these components were intentionally misplaced. Heating of the components in uniformly, even though it's in a non-equilibrium fashion, allows us time to reset the components both laterally and rotationally, enabling us to get a lot of value out of this. So This process gets very beneficial as we go into smaller component sizes and smaller solder pastes, as you don't need, for example, nitrogen environment. You don't need to have very precise pick and place placement for laser soldering and so forth.